When a black hole collides with an amount of antimatter equivalent to its size, a phenomenon called annihilation occurs, resulting in a powerful explosion. The energy of this explosion is proportional to the mass of the black hole, and for a typical black hole, it can generate energy equivalent to hundreds of quadrillion tons of TNT. Annihilation refers to the phenomenon where matter and antimatter annihilate each other, releasing electromagnetic waves and neutrinos. When a black hole collides with an amount of antimatter equivalent to its size, both the mass of the black hole and the antimatter participate in annihilation. Therefore, the energy released in the resulting explosion is extremely significant, capable of potentially destroying nearby space in the universe. The smaller the mass of the colliding black holes, the smaller the energy of the resulting explosion. For example, if a black hole with about 10% of the mass of the Sun were to collide, the energy released would be on the order of kilotons of TNT, comparable to natural disasters such as earthquakes or volcanic eruptions. The collision of black holes and antimatter is a phenomenon that can actually occur in the universe. Antimatter exists in space, and black holes continue to be formed after the Big Bang. Therefore, if two objects happen to meet in space, there is a possibility of collision. However, collisions between black holes and antimatter are extremely rare occurrences. Antimatter is very scarce in the universe, and there aren't many black holes either. Therefore, the probability of two objects colliding is very low. When a black hole collides with an amount of antimatter equivalent to its size, the two substances undergo annihilation. Annihilation is the phenomenon where matter and antimatter meet and transform into electromagnetic waves and two neutrinos. In this process, tremendous energy is emitted, equivalent to the combined mass of the matter and antimatter. Thus, when a black hole collides with an amount of antimatter equivalent to its size, the collision energy released equals the sum of the masses of the black hole and the antimatter. For example, if a black hole with the mass of the Sun and an equal mass of antimatter collided, the collision energy would be approximately 2 times 10 to the power of 30 J, or 200 billion trillion joules of energy. This is a tremendous amount of energy comparable to what the Sun emits over 10 to the power of 10 years. This energy is primarily emitted as electromagnetic waves and neutrinos, with some becoming photons and neutrons. Photons generate various forms of electromagnetic radiation, such as visible light, infrared, ultraviolet, X-rays, and gamma rays. Neutrons react with surrounding matter to produce radiation. The energy released due to the collision fills the surrounding space with photons and neutrons, leading to a powerful explosion. The magnitude of this explosion depends on the masses of the black hole and the antimatter. If a black hole with the mass of the Sun and an equivalent mass of antimatter collided, the explosion would likely affect an area of about 1,000 light-years. Furthermore, the photons and neutrinos generated by the collision can interact with surrounding matter, causing various phenomena. For instance, photons ionize surrounding matter, emitting electromagnetic waves, while neutrons react with surrounding matter to generate radiation. Therefore, the collision of black holes with amounts of antimatter equivalent to their sizes is an extremely powerful phenomenon in the universe, with significant consequences for the surrounding space. Although collisions between black holes and antimatter have not been observed yet, theoretically, the outcomes described above are expected. When a black hole collides with an amount of antimatter equivalent to its size, the two objects will undergo mutual annihilation. Annihilation is the phenomenon where matter and antimatter transform into energy when they meet. The energy released in this process is enormously large, estimated to be comparable to the energy emitted by the Sun throughout its lifetime. Therefore, when a black hole collides with an amount of antimatter equivalent to its size, a powerful explosion will occur due to the impact. This explosion will emit light millions of times brighter than the Sun and can destroy the surrounding space. The outcome of the collision depends on the masses and velocities of the two objects. If the masses are equal and the velocities are high, the two objects will completely annihilate, leaving nothing behind. However, if the masses are different or the velocities are slow, some matter may remain after the collision. In this case, the remaining matter could either form a new black hole or convert into light and energy. Although collisions between black holes and antimatter have not been observed so far, theoretically, the results described above are expected. The likelihood of annihilation occurring when antimatter and neutrinos collide is extremely low. Neutrinos are particles with very weak interactions, making the probability of colliding with antimatter very slim. Neutrinos have no charge and a spin of half. Antimatter, being particles with opposite charge, would require neutralization of charge for a collision with neutrinos to occur. Additionally, neutrinos having a spin of half would necessitate spin neutralization for a collision with antimatter. However, due to the very small mass of neutrinos, the probability of charge and spin neutralization is exceedingly low. Hence, the likelihood of collision between antimatter and neutrinos is very minimal. In reality, evidence of annihilation occurring from collisions between antimatter and neutrinos has not been discovered yet. Therefore, in a collision between antimatter and neutrinos, it's more probable that neutrinos would simply pass through antimatter. Nevertheless, due to the extremely high velocity at which neutrinos move, even if a collision were to occur, there's a possibility that neutrinos could pass through antimatter before annihilation takes place. Therefore, while annihilation could potentially occur when antimatter and neutrinos collide, the probability is very low.